Hi everyone, this is a pre-class video on module 2, that is symmetrical fault analysis. So, in this pre-class video I will be explaining whenever there is a short circuit across the generator terminals, so then how to analyze the problem of this kind, and here we are deriving how the subtransient, transient and synchronous reactances are changing with respect to time, and also I will be explaining the short circuit of a loaded synchronous generator and the selection of circuit breakers in this video. So, first we will see on no load. If there is no load is connected across the synchronous generator terminals, at those terminals if you consider the short circuit, then what will be the short circuit current wave shape with respect to time? See, this is what the short circuit current in the armature circuit at the time of fault. If you analyze this the wave shape, so in the absence of the offset DC component, the symmetrical short circuit current, it is looking in as shown in figure 2.3. The armature current under symmetrical three-phase fault can be divided into three regions, namely subtransient, transient and steady state. If you see this the subtransient current, so we are understanding the short circuit, how it happens. The theory behind this is very interesting. So, I will be explaining the theory behind the short circuit operation of the synchronous generator. A synchronous generator usually consisting of armature wound symmetrically of all the three phase on the stator, and also it has the field winding wound on the rotor. See, on the field structure we are placed the damper windings. These damper windings are placed in the pole faces the synchronous motor, which makes the synchronous machine self-starting. See, here the field structure is placed with the damping windings. The field winding is excited by DC supply, as we know. When the rotor rotates, the armature winding is cut by the magnetic flux of the field winding. Here the three phase alternating EMFs are induced in the armature winding. So, that in turn alternating three phase currents also set up in these windings, and this produces a rotating magnetic field which rotates at synchronous speed in the air gap. Here the field structure rotates at synchronous speed along with the rotating magnetic field produced by the armature winding. During the normal operation, what happens, the field produced by the armature currents will be relatively stationary with respect to the field and damper windings. Hence, the rotating magnetic field will not induce any voltages and currents in the field and damper windings during the normal operating conditions. That means, under steady state conditions, this is what happens. But when the alternator suddenly undergoes symmetrical short circuit under constant excitation remains same, but terminals are shorted, the short circuit armature current changes from 0 to very large value in all the three phases. The armature current will have an AC component as well as the offset DC component in each of the three phases. If we neglect the offset current, this is how the short circuit current will look like. So, in the y axis we have considered the symmetrical short circuit current, and x axis we have considered the time. So, as you see here, in the beginning we have more deviations, that is under subtransient condition. Under transient condition also we have a disturbance very less compared to the previous, and in the steady state the fluctuations are steady. Under steady state short circuit conditions, what happens? The armature reaction of the synchronous generator produces a demagnetizing flux. This effect is represented as the reactance called the armature reactance. The sum of the leakage reactance and the armature reactance is called the synchronous reactance. This is what it happens under steady state condition. Here, because of the demagnetizing flux, the effect it is consisting of only the armature reactance and the leakage reactance. In case of salient pole machines, the synchronous reactance is called direct axis reactance, and it is denoted by XD. Neglecting the armature resistance, the steady state short circuit model, it is looking like in figure 2.4. Here XD is XA plus XL. At the instant of short circuit, what happens? The DC offset current appears in all the three phases of the stator. This transient DC current will induce currents in the rotor field winding and damper windings by transformer action. The induced currents in these two windings will be in such a direction as to oppose the change of magnetic flux produced by the armature. This effect can be represented by having the two reactances in parallel with the XA. That means, see here, in the subtransient condition, what happens? So, along with XA plus XL, it is having two reactants, damper winding as well as the field. These two will contribute. Because of the short circuit, what happens? They comes in parallel, the overall reactance reduces. So, then what will be the total reactance? The total reactance will be the XL plus the parallel combination of these two. The equivalent value of these three reactants is this 1 divided by this value. So, because of this very less reactance, the subtransient current will be more. The combined effect of all these three reactances is to reduce the total reactance of the machine, and so that the short circuit current is very large in this period. It is called subtransient state. So, next in the total reactance of the machine under this condition as the subtransient reactance, that it is explained. So, now the induced current in both the field and damper windings decreases exponentially with respect to time, and depending on the time constants, that is L by R. The time constant of the damper winding is less compared to the time constant of the field winding, hence the induced currents in the damper windings dies fast with the few cycles. Effectively, XDW becomes open circuited, and the resulting reactance is called the transient reactance. In this transient reactance, as you see, a damper winding reactance value vanishes, and therefore the reactance offered will be much more compared to the previous one, and because of that the current will be less. The transient state model here we have, and then as you see XT single dash means transient, XT two dashes if you write in the previous that is XT double dash, that is subtransient state. Here XD single dash means transient, double dash means subtransient. The total reactance is given by, as you see here, total reactance is XL plus the parallel combination of these two, that is 1 divided by 1 by XA plus 1 by XF. The effect of the field winding current will also die out in the short time depending on the time constant of the field winding. This effect is equivalent to the open circuit of XF. Though if we then we will get this steady state reactance. So, from the 2-3 reactances we come to conclusion that the reactance under subtransient is very much less compared to the transient, and it is very much less compared to the steady state reactance. So, the various reactances of the synchronous machine can be estimated from the oscillogram shown in figure. The envelope of the current wave, this envelope of the current wave during the transient can be extrapolated. See here, this is transient state. So if you extrapolate it, it comes to B, subtransient C, and steady state if you extrapolate to the y axis, this is A. So 0 to A, that is here I will be the RMS value of the steady state current, and I dash will be the RMS value of the transient current, and I double dash will be the RMS value in the subtransient. If you extrapolate this, it will come to B. If you extrapolate this, come to A. So this steady state is nothing but OA by root 2. This is OB by root 2. This is OC by root 2. From this, can easily come to know that this is what. So the reactance XT dash, that is transient side, subtransient side reactance is nothing but voltage divided by current, that is subtransient current into volt, generator side. This is transient side, that is Eg by I dash. Steady state side reactance is Eg by I. So this is how we can find the expression for the subtransient, steady state and transient reactance values. Next, will this is what we have obtained. Now let us see the short circuit of a loaded synchronous generator. Loaded synchronous generator. Short circuit of a loaded synchronous generator. The determination of the short circuit currents when the machine is on load involves the determination of internal voltages behind subtransient, transient, steady state reactances. These are the voltages obtained by adding vectorically the subtransient, transient and steady state reactance voltage drops respectively due to the load currents IL to the terminal voltage V. So that means the voltages for the loaded condition synchronous generator is Eg double dash, that is subtransient, steady state and steady state, subtransient and transient reactance, that is terminal voltage plus this. Because this is a generator, excitation voltage will be more. So this is what this short circuit model of the synchronous generator under loaded condition. If you connect a load across the generator terminals, current flows through that. So then the formula Eg double dash here is the drop in the winding, that is XT double dash into IL plus V. This is the equation for this, because the load is connected here, load is connected, the terminal voltage is V, current flows through that. Similarly, if you consider the transient state voltage Eg dash, this is drop, that is J XD dash into IL plus V. And similarly, you can write this Eg for steady state, that is drop XD into IL plus V. Suppose if you consider the load is of synchronous motors, the internal EMF in the reactance is similar to that of the generator, except that the current direction is reversed in this. So therefore, if you motor action, if you consider, that is V minus, you will get V minus, because it is a motor action. So you will get V minus. This is very simple. Here if you consider the synchronous motors, this is a synchronous motor means it takes the supply from the source. This is a motor. If you consider motor, then it will take the supply. So, V will be more. So, V is equal to EM plus XD into IL, or EM is equal to V minus JXD into IL. So, similarly we can write this for subtransient study and the transient state. Next, let us understand how to analyze three-phase symmetrical faults. You can analyze the three-phase symmetrical fault by using Kirchhoff laws or Thevenin's theorem, or by forming the bus impedance matrix. Let us see these problems how to solve by using the Thevenin's theorem. Using the Thevenin's theorem, how to solve the problem. So, how to solve the symmetrical fault problem by using Thevenin's theorem. First, what we have to do is we have to choose the appropriate base values and we have to find the pre-fault condition reactance diagram. Just like in the previous module, that is module 1, there one line diagram, they will be giving all the component rating and winding connections. For that, it is required to find the reactance diagram that you have learned now. The same here we have to do. So, we have to find the pre-fault condition reactance diagram. Thereafter, where is the fault? At that point, we have to find the Thevenin's voltage, that is open circuit voltage at the terminals, and then we have to replace the fault point with the Thevenin's equivalent, that is open circuit voltage is nothing but Thevenin's voltage, and the impedance at that equivalent value of impedance at that fault point also it is required to find, that is Thevenin's impedance. By knowing this Thevenin's impedance and Thevenin's voltage source, we can find the fault current. That means, by knowing the Thevenin's voltage at the fault point and Thevenin's impedance, this is the fault point, let us assume. So, we can find the fault current. This is the fault current. So, the fault current is nothing but VTH by ZTH. So, after finding the fault current, we can find the current in other parts of the system. How to find the current in other parts of the system? To do that, we have to write the voltage source at the fault point, that is this value, and then we have to short the remaining sources, and we have to use Kirchhoff's voltage laws to find the current in the other parts of the power system due to the fault. Next, we will see how to select the circuit breakers. The circuit breaker is an automatically operated electrical switch which is capable of interrupting currents. Circuit breakers are high voltage, high current devices. So, if you consider the circuit breaker, there are two important computations we have to consider under short circuit conditions. One is rated momentary short circuit current, and the second one is rated symmetrical interrupting current. So, the symmetrical current to be interrupted is computed by using the subtransient reactances for synchronous generators and transient reactances for synchronous motors. Here the DC offset current value can be added to obtain the current to be interrupted is accounted for by multiplying the symmetrical short circuit current by the factor as tabulated here. So, the circuit breaker speed we have considered in the first column, and multiplying factor it is considered. So, 8 cycles are slower, then the multiplication factor will be 1. If the circuit breaker speed is 5 cycles, then it is 1.1. If it is 3 cycles, 1.2, and 2 cycles, 1.4. So, that means multiplying the symmetrical short circuit current by the factor, it is shown. The current that a circuit breaker can interrupt is inversely proportional to the operating voltage over the certain range. Amperes at operating voltage is given by the amperes at rated voltage multiplied by rated voltage by operating voltage. So, the circuit breaker rating in terms of short circuit MEA as shown here, it can be calculated by root 3 times of line voltage rated into short circuit current. The rating of the circuit breaker must be more than the short circuit MEA required to be interrupted.